Ho, 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 Merry Hackmas. Thanks for joining me today on the Qwerty Sage channel for day number 16 of the Advent of Cyber 2023 challenge. Today, we're going to dive more into machine learning. I'm really liking the challenges this year so far. Machine learning, out of all the topics, is the topic that I knew the least, little to none about. The math I get, the programming I get, the SQL I get, the honeypots, the firewalls. But machine learning and so forth, this is the most talked about topic. So I'm really loving it because the thing I knew the least about is the thing they're talking the most about. So day 14 and day 1, we looked at machine learning kind of on like a low to mid level, just like what it is, how neural networks work, and so forth. Day number 15, we looked at it defensively. We talked about how to use feed machine learning to find spam emails. We classified the emails as ham or spam, ham being legitimate, spam being illegitimate. And today we're going to use machine learning more on the offensive side. Now, I already recorded this, but last second, my recording software bugged out, didn't save things right. So I answered the questions, but we're going to do this again. So let's get to it. Can't capture this machine. McGreedy has locked Biscuity out of his LHQ admin panel by changing the password. To make it harder for Biscuity to perform a hack back, McGreedy has altered the admin panel login so it uses a CAPTCHA to prevent automated attacks. A CAPTCHA is a small test, like providing the numbers in an image that can be performed to ensure you're a human. This means McSkitty can't perform a brute force attack. Or does it? After his great success of using machine learning to detect defective toys and phishing emails, McSkitty is looking to you to help build a custom brute force script that will use machine learning to solve CAPTCHA and continue with the brute force attack. There is, however, a bit of irony in having a machine solve a challenge specifically designed to tell humans apart from computers. We're going to look at complex neural network structures. How does a convolution neural network function? We're going to use neural networks for optical character recognition and integrate neural networks into red teaming tools. So I already have the machine started up again. I'm going to walk through this again. I walked through it once, but I kind of want to share, document my journey and so forth. So I'm going to do it again. This is the login page we're going to try to crack or hack our way back into. It's our system. We got locked out of it by a hacker, so we're going to hack our way back in. Convolution networks, when yesterday we talked about garbage in, garbage out, and feature selection, and the importance of your data having good features. Convolution networks is built on the idea that you have nodes and the neural network itself uses the algorithms to extract features out of the data. So now, instead of making sure the machine learning is actually selecting what features it should be using out of it. We're not going to dive too much into the maths, but there is some math involved, mostly linear algebra. If you understand what matrices are, or read about matrices, because it doesn't explicitly say matrices in this lesson here, but it's using matrices. Um, we could divide our CNN into three components: feature extraction, which is the main topic for today. And we talked about fully connected layers and classification in the previous lessons. Fully connected layers are the hidden layers that you take an input and it provides the output. All the other layers, there's input layers that only that take the input in, but there's output layers too that provide output. But we're talking about the layers being the connectivity in between those hidden layers. Then we have classification, which was pretty much the ham or the spam. How are you classifying this? Are you classifying this toy as defective or good? In this case, the classification would end up being whatever number is in the CAPTCHA or whatever. So CNNs are used to classify images. Since we're using it to crack a CAPTCHA, we can look at this single letter in the CAPTCHA. PCs, computers, they look at images as just binary. It's binary, and each little small pixel in the image is a data point. The data can be described by its color. So it lists two ways that color can be represented: red, green, blue. Three 1-byte numbers from 0 to 25 indicated the intensity of the red, green, and blue in the pixel. Then there's grayscale, which is a single 1-byte number, 0 to 255, and 0 being white, 255 being black. Everything in between is a shade of gray. We could represent this image as a 2D array, and this is what it'll look like. They have the little grid here. There's other ways to denote colors. I know the people who are on the hue, saturation, light metrics would probably be like, what about us? But these are just the two ways they detail here, and that's kind of out the scope. Convolution is one of the first two steps of feature extraction. So pretty much it's going to enumerate or iterate or repeat these steps at least like one to a bunch of times, where it analyzes smaller size matrices or squares or 2D arrays, and it summarizes the information in the bigger array down into a smaller array to make it a little bit more palatable. That's what convolution really is. There are two reasons for convolution. If you create a neural network that takes each pixel as input, this would be incredibly large, and it wouldn't improve the accuracy. The summary created by convolution allows you to still capture the image important details, but you don't need all the fluff, all the extra data. That's not going to provide any more efficiency. Actually, it'll be less efficient because now you're working with a bigger size of things and you have to go over more. So it's going to be slower and it's not going to be more accurate. The term for this is called sparse interaction. And there's more information. If we capture a feature in one location, it will be just as useful as a feature in the other location. So, making use of the same kernel to determine the summary slice means this condition is met. When we update the weights in one of our kernels, it'll alter the summary for all the pixels. So, if it occurs for one, it should occur for them all. So, instead of making a bunch of changes, You can make one change and it'll be applicable to all because the same property should apply to all. This results in something called the property of equivariance to translation. Simply put, if we change the input in a specific way, the output will also get changed in that same way. If you want to learn more, there's more information here. Then there's pooling, the second step performed by the CNN, or the convolution neural network. Similar to convolution, pooling aims to summarize the data using a statistical method. Now, in this example, it'll take a slice and it'll do max pooling, which will provide a summary of the maximum values. So we have a 4x4 grid here. It's going to summarize it into a 2x2 grid here. And let's just say you have like north, south, east, west, or top left, top right, bottom left, bottom right. It's going to find the maximum number in here, which is this. The maximum number here, F9, the maximum number here, E9, and the maximum number here, which is C0. And it's going to put that into a 2x2 as demonstrated. And for max pooling, this is finding the maximum value. We could use a different statistical method, such as average pooling, where you find the averages of all these numbers and you put it in like that. But there's different strokes for different folks, and you just have to use whatever methodology fits your use case to provide the most efficient, accurate, effective result. Fully connected layers. Now we have our features. The next stage is similar to the basic neural network structure we used. We'll create a neural network that takes the inputs, runs them through the hidden layers, and then provides the output. This is called the fully connected layers portion of the CNN. At this point, the neural networks where each node is reconnected to all other nodes in the next layer. Then we have classification. Now the classification on this one is different because in the previous examples, you pretty much had a true-false situation, defective or not, spam or not, so forth. In this case, you need an output node for 0 to 9 because these CAPTCHAs are numbers only. If it was letters and numbers, it would be 36 if just uppercase or lowercase. If both uppercase or lowercase, it'd be 62. And some of that was talked about in the first couple lessons, the first brute force lesson, day 2, day 3. We talked about kind of how having a bigger key size or more entropy can give more combinations or permutations, combinations that you can work with as far as data sets, passwords, and etc. goes. Having multiple outputs creates an interesting feature. Instead of simply getting one answer, all 26 outputs will have a decimal value between 0 and 1. We'll summarize this by taking the highest value answer as the answer. However, nothing is stopping us from reviewing the top 5 answers. This can help us identify where the network is having issues. For example, there could be confusion between like the letters M and N. They look very familiar. The letter M to a computer actually might look like an N and a half or 2 N's or just even 1 N, depending on how well it's embedded in the CAPTCHA and the data sets and points. Sometimes I confuse like the number 1, a lowercase L, and an uppercase I. They could look the same, especially in isolation. If it's next to like a letter D or a letter B or a letter K, then I could say, oh, okay, I could see better like the height variances and stuff. Training our CNN, we covered the basis. We're going to train our CNN. We're going to use attention OCR. for our CNN model. The CNN structure is a lot going on, such as LSTMs and slider windows, but we're not diving deep into that things. We're going to make use of the same steps to create CAPTCHA 22, which is a pip package. Use a CAPTCHA Kraken server. You can read more here. In order to create CAPTCHAs, we're going to go through these steps. We're going to gather the CAPTCHAs to create the labeled data, label the CAPTCHAs in order to use a supervised learning model, train the CAPTCHA Crack CNN, verify, test our CAPTCHA Kraken CNN, export and host the training models so we can feed the CAPTCHAs and create and execute a brute force script. Now, we're not going to be doing all of these things. Some of these things are very time intensive, resource consuming. Some of these things are already done. All right, so we're going to hop to it. Start with our Docker container. So, Docker run the volume on our local machine is the volume is going to be that. We're going to map it to Tinder. The volume on the container. ARCR full. All right. And we have a hash. This is the container ID. This is the ID of the container. If you do a Docker PS, that'll show you the containers runner. And you see the first few characters of that container ID. I'm going to copy that. You're going to hop inside the container and get a shell. IT, because it's going to be an interactive shell. Paste. There we go. Bin that bash. So we're going to get a bash shell. Born again C shell. By the seashore shell. All right. It wants us to go to the OCR folder. And we already looked at the portal we're going to crack. We're going to issue a curl statement. And what curl's going to do is pull down the HTML file just like your browser does. It's exactly what your browser does. But your browser takes the data that we get from here you know what? We need to do that in this shell. TryHackMe Court 8000. So we got some interesting information here on the ported, the real ported thing to know. Outside of, I recommend everybody, if you're into this type of stuff, you should know the basic syntax for like HTML. Like you should be able to make like a simple website, even if it's just like hello world with like a yellow background that changes to pink after 5 seconds and that's it. Like you should be able to know how to do that. Yeah. That's not really asking too much. There's tons of resources on that. But image in Space 64 coded. If you've been following along, you've probably seen that. And this is really like all the image data. This is like the CAPTCHA here. All of that gets translated into this little picture you see here. All right. So, Let's see. This looks like something we need to do inside the Docker container, but yep, it is. Yep. All right. So we're gonna print the directory, the contents of the directory raw data set, and we're gonna look at the attributes. We're gonna make it long, and we're gonna include hidden files, data sets. Uh, I did not include the final. All right, it's all right. So that's already done. That is all the pictures, the PNGs that end up being the CAPTCHAs. So next is labels, and that's already done too. But if you wanted to do it yourself, you run this command. But let's just look at some of the training data labels. Training.txt. So these are the labels. So pretty much this is saying for this picture here, we should be getting this result for the output from our neural in our neural network. And that's for training and validation. It's supervised training and supervised training. You should always have a data set with the proper results that is expected to feed to the AI, our machine learning, to help it improve its models. All right. It looks like now we're going to get down to business and we're going to train it. Oh, it's already trained. So it's already trained. And you could run this command and train it again. But so now that it's already trained, we can test it. And it looks like in this one, we are gonna test. We are gonna test. So a OCR test testing dot TF records. The important thing to realize here is we have an accuracy number, a loss number. This is the amount of times the rate that it got it wrong. Um, so this would be like 67%. This would be like 0.04%. Perplexity is like how difficult, how sure it thinks it's right. Um, the closer the one, the better. The higher the number, the more unsure it is. And that should kind of correlate with the probability. All right. All right. The testing did not like me. Because we wasn't in the right folder. Yeah. So in this command, there was the change directory to labels. And because we weren't in that folder, it did not see the testing.tf records file. So now we changed the directory. Let's run it again. Once a couple testing steps are complete, you can stop it using Control C. So it looks like a few cycles did complete. So you notice that went really a lot faster than training it would have went. So we tested 252, accuracy 99.76%. The loss really low, really low. The perplexity is really low too. It's very close to 1. All right. All right. So we're going to get close to hosting our CNN model. So the first thing we're going to do, we're going to export. We're going to export the model that we have now. So and these 2 ampersands, that's end. So when we're going to run this command, and then it's going to, after that command's done, it's going to run this command. So you don't have to type in this command and then wait for it and then type in this. We'll just put it on one line. So we're going to copy recursively model, and we're going to put it in temp there, which let's see. No, we won't see it there. All right. Well, once that's done, we're going to exit anyway. So let's make sure that it's actually there. All right, good. It's there. It is there. Yep. And the subfolders are there too, which is why we have that OR flag. That means don't just copy the folder, but copy any of the folders inside the folder, and any folders that may be inside those folders, and it's recursive. So anything that's in it, otherwise it'll just copy whatever's just in the directory. You know, could miss the subfolders. So we'll exit Docker PS, Docker. Well, kind of wanted to show you that temp there folder. So if you go to temp data, we mapped it to temp there in that Docker container. So when we moved it to model, we actually moved the model inside this folder. We can verify that in a second. We can definitely verify that too. So it's kind of a Docker course too. Well, the lesson isn't about Docker, but if we want to use Docker, it's probably good to understand some of these basic commands that we're running here as well. All right. If we run Docker PS, that should be done. Where did I say it was? Going to list this. Yep, you see the model data is there. So we're going to take that model, we're going to feed it into a new Docker container running TensorFlow. And with that, we'll be able to have, you should be able to come to here and see that the API is being hosted at this URL here. And then we can feed it the CAPTCHAs from the web page when we try to brute force it. All right. Very well. Paste those. Make sure I don't need to change any of this information. So yeah, that's the model information, the exported model. We're going to put it in the models folder under the root of the Docker container. All right. We're going to let that cook. Let that cook. We're going to let that cook. All right. Give it a brief moment. While we're giving it a moment, it might take a second before it really starts listening on that port, which should be about now. By the time we type it in, we'll be good. OCR. All right. And it says available. That's good. That's good. It says available. All right. So we have this Python script on the desktop. So on the desktop, let's go ahead. Change it to desktop. And let's brute forcer. All right. So it ports request. What the request library is going to do is allow us to make the HTTP calls to the API. Like when you go to a website, you're doing an HTTP request. It's going to do that for us programmatically. Base 64 is going to help encode the file into that base 64, which you see is in the model. JSON is just going to help us submit the payloads to the API. And Beautiful Soup 4, what Beautiful Soup 4 is going to do for us is all this HTML that we get from the website from when we did the curl command. It's going to help turn that into structured data that we can manipulate in our Python. Username admin, passwords. This is the website we're trying to crack. This is the site that's hosting our machine learning model that we're going to use to feed the CAPTCHAs. It's going to open it, password.txt file, and it's going to save it in the passwords array. Access granted is false. While access granted is false and the count is less than the number of passwords, the password is going to equal passwords that count on the count index. So it's going to start at 0, and I guess it's going to increment every time. So it should be a count plus 1 command somewhere in this loop. So it's going to get the session. It's going to save the session information from the website. It's going to parse it with the Beautiful Soup. It's going to find the image using the image tag in the HTML that I pointed out. So it's going to find this tag. Because we use Beautiful Soup, You can access it just like a Python data structure. It's gonna encode, so it's just gonna get this information, this gobbledygook. The model, signature input. So it's gonna put the encoded image information here, which this is already base 64. Then it's gonna post. The prediction is gonna be in the response. Okay. So if we are not more than 90% sure that we're getting the right answer, we're not going to submit the CAPTCHA. We're going to continue. So what that's going to do, that's going to start the loop over, but it's not going to increment the count. So it's going to use the same password again, but it's going to get a new CAPTCHA that we're going to be more likely to crack. And because we don't submit the CAPTCHA, sometimes when you have CAPTCHAs, the authenticating server will be logging failed CAPTCHA attempts. And we don't want to have, if you're a real red team or a hacker, you don't want the person having, wait, where are these 20,000 failed CAPTCHA attempts? Because that's going to put someone on your trail. Now, I don't know why we would need it in this case, because in this case, we're hacking into our own system. Preferably, you would be hacking into your own system. I don't advocate for any malicious behavior out on these webs. Hack your own stuff, get permission, get a job where you can get permission. There's avenues around this without risking, jail time. Anyway, website data, username, password, CAPTCHA, answer. So if the probability is greater than 90%, it'll go below here. If it's less than, we're not even getting this far. So it's making a dictionary item, which is gonna send in a post request to the website, and then it's gonna get the response. If incorrect CAPTCHA value supplied in response, it's gonna print incorrect CAPTCHA value, will resubmit. So then continue. So it's gonna do the same thing here if the CAPTCHA was wrong. But this is, we were kind of positive we would have the right answer. So now we're positive, but it was wrong. So let's run it again with the different CAPTCHA. This is incorrect username or password. It's going to increment the count. So now this is going to make it use the next password in our list of passwords. Otherwise, we found the correct password and we had the right CAPTCHA. And the access granted is true. And we're going to print out the username and the password. This pretty much explains everything I just said. I deep dived it, and it's a succinct explanation, but sometimes it's good just to do a little walkthrough like that. So now we run it. We're already in the brute force folder, so we just need to run brute force.py, and we should be done with this challenge. So let's brute force. It's a subfolder. That's right. Force. All right. We do Python 3 forcer.py. Now should be right in the world. You got a couple incorrect paths. So the password is really not going to guess this username admin. So let's refresh this, get a new CAPTCHA. Admin. Really not going to guess this. Yes, copy and paste that. All right, let's see if I can read this hodgepodge. All right, and there we go. We got the flag. We hacked into the website. We cracked the CAPTCHA automatically, and bing bam. So the questions already answered, but let's read them. What's the key process of training a neural network that is taken care of using the CNN? That's feature extraction. What is the name of the process used in the CNN to extract the features? It's called convolution. What is the name of the process used to reduce the features down? Pooling. What off-the-shelf CDN do we use to train a CAPTCHA cracking OCR model? We used Attention OCR to train the model. We hosted the model with TensorFlow in a Docker container. Well, we trained the OCR in a Docker container too. What's the name of the password McGreedy used to set the HQ admin password? Really not gonna guess this. He's a very original dude. What is the value of the flag that you receive when you successfully authenticate to the HQ admin portal? And that is this guy here. And that's it. That's day 16 of the Advent of Cyber 2023 challenge on TryHackMe. We looked at a lot. Machine learning. We looked at Docker some. We did some Linux command line stuff. We did some brute forcing. Looked at optical character recognition. We evaluated Python scripts. Like, the sky's the limit. This was a pretty beefy lab. Like, you talked about matrices. Like, I haven't really talked about matrices that much since I took the linear algebra course back on the good Bluff University. Yeah. All right. Well, thanks for tuning in, guys, and have a great evening.